speak about the Ricci curvature fundamental group. There are notes for the lectures on my webpage under teaching, and the notes contain much more than what I will be able to cover. So let me just start as a kind of motivation by reminding you of a classical theorem to give you an idea of where we are heading. This is the Bonnet-Myers theorem. And it says that if you have a manifold with a strictly positive lower bound on the Ricci curvature, and up to normalization we can assume that the Ricci curvature is greater or equal than n-1, then the fundamental group of the manifold is fine. Okay, so the proof is very classical. If you have a manifold with a strictly positive lower bound on the Ricci curvature, then the diameter must be finite. A strictly positive lower bound on the Ricci curvature is inherited by any cover, in particular by the universal cover. And this is telling you that the universal cover of any such manifold must be compact, and therefore the fundamental group must be finite. Okay, so the idea for the course is going to be that I would like to discuss similar abstractions for manifolds with non-negative Ricci curvature. Okay, and for most of the course I'm going to focus on the case where the manifolds are non-compact. But to begin, today I'm going to start with the compact manifold. Okay, you should feel free to tag me anytime if you have comments or questions. So let's start with the definition, which probably you all know. So given a metric space XV, a line, a ray in X is a curve gamma from 0 plus infinity to X, such that distance between gamma of S and gamma of T is equal to the absolute value of S minus T for every S and T in the domain. Okay, and a line is the same thing, but this time I replace the half line with the line, and the requirement is the same. Okay, so one of the very first and most classical structural theorems about manifolds with a negative Ricci curvature is the so-called splitting theorem, due to Shiger and Gromov in 1972. And the theorem says that if a smooth Riemannian manifold MNG with Ricci greater or equal than 0, and I'm going to assume for all of the course that the manifolds are all complete smooth and complete, and the exponent here is going to denote the dimension of the manifold. So if such a manifold contains a line, then it splits isometrically. This means that M should be equal to the Riemannian product of a line with a manifold of dimension n-1. Okay, and from the well-known formulas for the Ricci curvature, it follows in particular that this factor here should have a Ricci curvature, non-negative Ricci curvature as well. Okay, so a straightforward corollary of this Shiger and Gromov splitting theorem is the following. So if you have any manifold with a negative Ricci curvature, and such manifold can be written as a Euclidean factor, k times a factor n of dimension n minus k in such a way that the Ricci curvature of n is greater or equal than 0 and the factor n contains no line. Okay, so this is straightforward once you are given the Gromov splitting theorem. The reason is that you can just apply iteratively the splitting theorem until you have killed all the Euclidean factors. Okay, so in such a context, when you have a product of a Euclidean factor with a factor containing no lines, then the isometry group of the manifold is pretty well behaved in the following sense. So if M is equal to Rk times n, and contains no lines, then the isometry group of the big manifold M is equal to a direct product of the isometry group of the Euclidean factor with the isometry group of the factor not containing any line. Okay, and this is going to be very helpful for us in a minute. I won't prove the statement. I'll leave you the proof as an exercise. Okay, and the idea is very simple. The idea is that since the notion of line is a metric notion, okay, you can easily check that isometries must map lines to lines. Okay, so let's use this lemma, this corollary, to get some restrictions in the context we care about. So here is the proposition. So the proposition says that if M and G is closed, means compact, with Ricci greater or equal than 0, okay, then the universal cover splits as a Euclidean factor times a factor containing no lines, and the non-trivial part here is that this guy, let me call it n bar, should be simply connected. And this is obvious. The non-trivial part is that this factor containing no lines is also compact. Okay? So let's see how we can combine the previous ingredients to prove this proposition. Okay, the proof starts by applying the corollary. So you can apply the corollary and write m bar as the maximal Euclidean factor times a factor containing no lines. Okay, so it's clear that, as I said, n bar must be simply connected because the product is simply connected. Okay, the corollary only tells us that n bar contains no lines. Okay, and I claim that n bar is compact. Okay, so let's prove this by contradiction. Okay, so assume it is not. Okay, so if you have a non-compact Riemannian manifold, then if you fix any point, you can certainly find the ray starting from that point. Okay, so now, so the idea is geometrically very clean. So you have this base point. So let's say that C of 0 is is equal to x. Here you have your base point, x, you have this ray. Okay, and the idea is that if you stare at the ray and you look at it from a base point which is very far apart, this ray is going to look more and more like line. Okay, so now we can define a sequence of segments Ci from 0 to I into m bar by setting Ci of t to be, so I fix the first coordinate, the coordinate in the Euclidean factor, to be 0, and then I take the second component to be the original array that I was starting with. Okay, now since I need to use my assumption, the assumption was that the manifold, the original manifold is closed, and in particular it has finite diameter. Then for any I in n, I can find gamma I, an element of the fundamental group of my manifold based X. Such that the distance between 0x and gamma I of Ci of I is smaller than the diameter of the quotient manifold. Okay, now basically what I did was to bring all the points C of I back to a fixed compact. Okay, and now what I can do is I can pass to the limit. So up to some sequences. C tilde I from 0 to I to m bar, defined by setting C tilde phi equal to gamma I composed with Ci, converge to a line. In m bar. Okay, but now I can use the lemma, which says that isometries of a Riemannian manifold which splits the Euclidean factor and the factor containing no lines split. Okay, and so all these segments, and therefore also the limit line, have a very special form. They are all segments into the factor m bar, and therefore when I pass to the limit this condition, I actually get a line. In my factor n bar. Okay, and this is a contradiction because to start with, I was assuming that n bar contained no lines.
Sorry, how do you pass from having, so these are like the Ci tildes are part of rays?
Yeah.
I mean, is this C tilde the limit not from 0 to?
Oh, sorry, I need to reparameterize that in such a way that at 0, okay, the value is this point.
Ah.
Okay. Sorry, thank you.
Can I have a question?
Please.
What are these gamma I's?
So they are elements of the fundamental group. Okay, you should think of them as isometries of the universal cover. Okay, and since the quotient manifold is compact, and in particular it has finite diameter, for anything that you are on Rn, let's say, on R2, okay, and the manifold you started with is a torus. Okay, so the universal cover is non-compact, but the quotient is compact. Okay, and if you think of the fundamental group as acting by isometries on the universal cover, okay, then what's going to happen is that if you fix any point, if you fix a base point here, and if you fix any other point in the universal cover, there is going to be an isometry in the fundamental group, bringing this point to a distance from the original one, which is smaller than the diameter of the quotient. clarify things? Okay. Any more questions?
Could you go with the convergence again? Like, why would it?
Okay, so now, sure. So I have a sequence. This is a consequence of Ascoli-Arzel's last theorem. Okay, so say that I reparameterize the C tilde I correctly in such a way that C tilde I of 0, the distance between C tilde I of 0 and 0x is less or equal than the diameter of L. Okay, now what happens is that the curves C tilde I are uniformly continuous. Okay, this follows from the fact that they are raised. So namely, the distance between C tilde I of S and C tilde I of T is less or equal than S is actually equal, but I only care about the less or equal inequality. Okay, so gamma is an isometry, okay, and C is a ray, so therefore C satisfies equality here, and I am applying an isometry, and therefore the inequality remains still there. Okay, and this is telling me that all the curves C tilde I are uniformly continuous. Okay, they are Lipschitz in particular, uniformly equal Lipschitz. Okay, so I have a sequence of curves from an increasing family of intervals into my manifold. They are uniformly continuous, and at 0 they all go through a sequence of points which are a bounded distance away from my base point 0x. Okay, now I can apply Ascoli-Arzel's last compactness theorem to pass to a limit. Okay, and in the limit, all these conditions pass to the limit, and therefore I get a line. Better now? Please.
So the way we are using that fundamental group is not, it is a finite quantity there. So why finiteness of fundamental group?
No, I'm not using that the fundamental group is finite. I'm only using that the diameter of the original manifold is finite. Okay, and this I need in order to bring back an arbitrary point, okay, to a fixed compact region. Okay, so the picture is the following. So you have 0x here. Okay, and now I look at the point Ci of I. Okay, and I would like to bring this point in a fixed compact set near to 0x. Okay, in principle, if I'm staring at a random manifold, there is no way to do that. Okay, and the fact that the quotient, so M is the universal cover, M bar modulo the fundamental group. Okay, the fact that this quotient is compact, okay, tells me that there is an element of the fundamental group, i.e. an isometry of the universal cover, such that gamma I of Ci of I, okay, gets back into this compact set. Namely, the distance between this point and 0x is less or equal than the diameter of M. Okay, so this is the place where I'm using that the quotient is compact. Please.
You mean pi 1 of M?
Yeah, exactly. Yeah. Thank you. Any more questions?
Why will we get equality, not just inequality?
We get equality. So in order to use Ascoli-Arzel's last theorem, we only need the inequality. Okay, but in the end, if we want to check that the limit guy is a line, we need the equality. Okay. Any more questions? Please.
We define C tilde as a limit of the Ci tilde, so
yeah.
which are defined on
yeah.
interval from 0 to positive numbers. So
actually, I reparameterize them in such a way that they become defined on minus I. Okay. Any more questions? Okay, now, so let's see how we can use this theorem to get some restrictions on the fundamental groups of those guys. But so first, let me stress that there is a straightforward corollary of the proposition, namely the following. So if M and G is closed with Ricci curvature which is greater or equal than 0, and the fundamental group is infinite, okay, then there exists P inside the manifold and a non-zero vector in the tangent space. Such that the Ricci curvature at that point in the direction is 0. Okay? And what's the reason? The reason is that we can apply the proposition. Okay? If the fundamental group is infinite, there must be a non-trivial Euclidean factor. Okay? But now, if you look at the Ricci curvature of such a product, in the direction of the Euclidean factor, this vanishes. Okay? Any questions?
Is it sharp estimate that only one?
No, no, it's not sharp. It's not sharp. Okay. But of course, you're going to get it for all points in the manifold. There is going to be a vector. The vector going in the Euclidean direction, such that the Ricci curvature at that vector is equal to 0. Okay. But what I wanted to stress is that there exists at least one, and this is going to come back later. Okay. Any questions? Okay. So let me discuss another. More surprising application, so more interesting application of this proposition. Okay, so I would like to apply a proposition to convince you that there are, so to give you an example of a compact manifold which does not admit any metric of non-negative Ricci curvature. Okay, so we start from the following. We consider the so-called Heisenberg group. Okay, this is the group of upper triangular matrices with ones of the diagonal. Okay, so this is a subgroup of the general linear group in dimension 3. Okay, so this is the Heisenberg group. Okay, it is not abelian. One simple reason is that if you compute the commutator between 1 and now you choose the only non-trivial element to be this one. This gives you this element here. Okay, so there are two non-computing elements, so it can be abelian. However, it is nilpotent with nilpotency length 2. Okay, so let me remind you of what that means. Okay, so G is nilpotent if the central series defined starting from G0, which is equal to G by definition, and then defining Gi plus 1 to be the group of commutators between G, all the group, and the guy that you obtained at the previous step, Gi. Okay, so this sequence of subgroups of G is called the central series of G, and the requirement for G to be nilpotent is that this series finishes after finitely many steps. Okay, and the minimal natural such that Gi Gk is equal to the identity is called the nilpotency length of the group. Okay? So now the Heisenberg group with real coefficients emits a co-compact lattice. So we can consider the Heisenberg group with integer coefficients as a subgroup. Okay? And this is defined in the obvious way by replacing the requirement that A, B, and C are real with the requirement that A, B, and C are integers. Okay? So this is a discrete subgroup. And what happens is that if you look at the quotient space, H3 of R modulo H3 of Z, this is compact. Okay? And it is called the Heisenberg manifold. Okay? Any questions?
When you say it forms a lattice, do you really need just the identification with the set of points in the R3 space?
Say it again, sorry.
When you say it forms a lattice,
Uh-huh.
you just mean the identification with the in R3.
So the definition of lattice is that it is a discrete subgroup. Okay, and for us, so there is a general definition, but in our setting, what I care about is that the quotient is compact. So for today, a lattice is going to be a discrete subgroup, such that when you look at the quotient of the group you started with respect to the lattice, you get something compact. Okay.
You want the quotient to be smooth also? Or?
So the quotient is going to be a manifold. Okay, and this you can. So in this case, or in general, for the general definition.
No, for definition.
Okay, for the definition, it follows that it is a manifold. Okay, but we will not care about it. In this specific case, you can check directly that it is a manifold. Any more questions? Okay, so note that H3 of R with its natural group operation is not isomorphic to R3. With addition. Okay, however, the underlying manifold is diffeomorphic to R3. Okay, moreover, this is a general fact. If you look at the fundamental group of this guy, okay, this is going to be isomorphic to the lattice. Okay, now I claim that there exists. Thank you. Thank you. So I claim that there is no G, metric G, with Ricci greater or equal than 0 on S. Okay? And how does the proof go? Okay, so I told you that the universal cover is diffeomorphic to R3. Okay, now I can apply the proposition.
What is N?
N is the Heisenberg manifold that I defined here. Okay, I didn't call it N. Thank you. Thank you. So if I apply the proposition, then what I get is that the universal cover is isometric to R3. With the standard flat method, that we call G Euclidean. Okay, but now the fundamental group, you can view it as a subgroup of the isometric group of the universal cover. Okay, and this would imply that the isometric group of R3 as a subgroup isomorphic to the Heisenberg group with integer coefficients. Okay? And there are several different ways to check that there is no such subgroup. Okay, I leave this to you as an exercise. Okay? Any questions?
What did the previous propositions mean?
So the proposition, I think I erased this, so it's the proposition which says that if you have a closed manifold with non-negative Ricci curvature, okay, you look at the universal cover, then the universal cover is going to be a Riemannian product of a Euclidean factor with a compact simply connected factor. Okay? Any more questions? Okay, so actually this is just an example which was meant to illustrate a more general theorem that Chiger and Gromov proved. Which says that if M and G is closed with the negative Ricci curvature, then I1 of M as a subgroup with finite index isomorphic to K for some K between 0 and the dimension of solution. Okay? So let me introduce some terminology. So in the sequel, we're gonna say that a discrete group gamma is virtually zk or virtually abelian or virtually nilpotent if it has a finite index subgroup isomorphic to zk or abelian or nilpotent. Okay, so we could replace Chiker and Gromov's statement by saying that the fundamental group of a closed manifold with non-negative Ricci curvature is virtually zk. Any questions?
May I ask, is there a geometric interpretation? How can one determine what is K?
Okay, so this is a good question. So K here is the dimension of the Euclidean factor that the universal covers space. Okay, does it answer to your question? Anyone? Please.
What's the definition of a discrete group?
A discrete group, it's a topological group endowed with a discrete topology. Okay? And such that the discrete topology makes it a topological group. Okay? So you would like that the group operations are continuous. Okay? Any more questions? Okay. So now the next thing that I would like to do is so to convince you that the assumption that the manifold was closed at the very beginning was crucial for both this corollary here and this theorem here. Okay? So let's discuss an example. This was constructed by Nabornan in 81. Okay, what he did was to construct a metric G, which is a Riemannian, smooth and complete, with everywhere positive Ricci curvature on R3 times the circle. Okay? So, in particular, note that this manifold has fundamental group isomorphic to the fundamental group of the circle, which is infinite. And so, what he got was the first example of a manifold with positive Ricci curvature and infinite fundamental group. Okay, so if you remember, the corollary here told us that the closed manifold with infinite fundamental group and non-negative Ricci curvature has a 0 for the Ricci curvature. Okay, and this example tells you that if the manifold you start with is not closed, then the corollary doesn't hold anymore. Okay, so, and actually, once someone tells you how to construct the metric, constructed it is an exercise in Riemannian geometry. Okay, so the metric G on R3 times this one is of the form G equal to d r squared plus the so-called warping function f of r times the metric on S2 plus another warping function times the metric on the circle. Okay? So note that if you just take the Riemannian product of the flat metric on R3 with the unique metric on the circle, you get a metric with non-negative Ricci curvature, but with many zeros for the Ricci curvature. Okay? And note also that if you choose R, f of R equal to R here, then this component is giving rise to the Euclidean metric on R3. Okay, and analogously, if you choose this function here to be a constant, okay, then you would get a Riemannian product of this metric with a metric on the circle. Okay, so and the exercise that I leave to you is to find suitable f and h such that G has positive Ricci. Okay, so the idea is that the only metric on the circle is the flat metric, and this would introduce zeros for the Ricci curvature. Okay, now you use in the clever way the fact that the metric on the two sphere has positive Ricci curvature to compensate for the zeros of the Ricci curvature coming from this piece here. Okay, any questions? And so it turns out that also Schiller and Gromov's theorem cannot be generalized to manifolds which are not compact. And indeed, Way in 88, and her statement was subsequently refined by Wilking in 2000. Proved that if gamma is finitely generated and bigger in nilpotent, then there is a manifold and G with everywhere positive Ricci curvature and one of them isomorphic to gamma. Okay? So in particular, if you go back at the example we discussed a few minutes ago, so the Heisenberg group with the integer coefficients is nilpotent. Okay? It is finally generated. It is generated by the two matrices that I mentioned before. So the one on those with the ones only in one spot. Okay, so you can apply this theorem and you get a manifold with positive Ricci curvature everywhere, with fundamental group isomorphic to the Heisenberg group with integer coefficients. Okay, so as in the previous case, this is showing that the assumption that the manifold was compact was crucial for those statements. Any questions? Okay, so the next thing that I would like to discuss is related to the sharpness of this statement. Okay, so this requires some background.
That's the question.
Sure.
So in the example
matrix R3 times S1. Is this the lowest dimensional known example? Are there like a lower dimensional one?
I think I should check, but I think that in lower yeah, I think this is true. Yeah, this is the lowest possible dimension where such example can exist. So if you have so in dimension 2 this is classical, in dimension 3 this is much more trivial. But if you have a manifold with infinite fundamental group in dimension 3 and non-negative Ricci curvature, then there are zeros for the Ricci curvature. Okay. Any more, please?
For the Heisenberg group, some specific Heisenberg group, do we know what kind of manifolds would we get?
Yeah, yeah. So the construction starts from a similar idea. Okay, so you construct the universal cover first, and the underlying manifold. Let's say that we look at the Heisenberg group with integer coefficients. Okay, so the universal cover is going to be diffeomorphic to Rk times the Heisenberg group with real coefficients. Okay, which, as I told you before, is diffeomorphic to R3. Okay, so this is diffeomorphic to Rk plus 3. Okay, now what you do is you choose a metric of the form dr square plus f of r square times g of the sphere of dimension 1 k minus 1. So this is similar to what Nabonan did right there. Okay, and then here you choose a family of matrix G tilde R. Okay, this should be matrix on the Heisenberg group, which are invariant on the left. This is a group, so it makes sense to consider left invariant matrix. Okay, if you pick left invariance matrix on the Heisenberg group. Okay, so since they are left invariant on all Heisenberg group, they are invariant under the action of the Heisenberg group with integer coefficients. Okay, and so you can take the quotient. So you let M be M bar modulo H3 of Z. Okay, and this M is going to have fundamental group isomorphic to H3 of Z. Okay, what's non-trivial, of course, is finding suitable left invariant matrix here. Okay, and choosing appropriately this factor, this working factor here, in such a way that the Ricci curvature is positive. Any more? Okay, so I need some terminology in order to discuss the developments that show how such theorem is sharp. So I need to tell you what a work metric on a group, on a discrete group is. So say that gamma is finally generated. And I choose a symmetric generating set S with finitely many elements, so gamma 1, gamma k. Okay. Then I define the work distance between two elements of the group, G and H, to be the minimal of the set of those N in N, such that there exists gamma I1, gamma IN in the generating set with G equal to gamma I1 times gamma IN times H. Okay? Any questions on the definition?
What does symmetric?
Symmetric means that if gamma belongs to the generating set, then gamma to the minus 1 belongs to the generating set as well. So it's closed under taking the inverse. Any more questions? Okay, so I leave you as an exercise, okay, to check that this is actually distance. Okay, so this is part A. And part B answers to another question, namely, how much does the distance depend on the choice of the symmetric generating set? Okay, and the answer is that if S and S prime are both generating sets, okay, and you look at the induced work matrix DS and DS prime, okay, then they're going to be by Ricci. Okay, which means that the identity from gamma with the distance ds to gamma with the distance ds prime is a bi-Ricci. Okay? So, starting with this notion, I can tell you what a group of polynomial growth is. So, a finely generated gamma as polynomial growth of degree n. If, when I look at the ball with respect to this distance, centered at the identity, this ball should have less than a constant times r to the n elements for every radius which is bigger than 1. Okay? So here, see, there is an continuous fixed. Okay, and this is the metric ball centered at the identity with respect to the word metric. Any questions on the definition? Okay, so now I can state an important theorem that Miller proved. So Miller is 68. Prove that H M and G as Ricci greater or equal than 0, and gamma is a finely generated subgroup of the fundamental group. Then gamma as polynomial growth of degree n. Okay? Do I have 5 more minutes? Okay, so let me finish by proving this theorem. Okay? At most times. So the definition that in the definition that I gave, so this is quite flexible. So I say that it has degree n. Okay, if this is bounded by c times r to the n. So also linear growth will be fine with the definition. Okay? Does it answer? Okay, so let's sketch the proof of this theorem. So consider, so as before, we view gamma as a subgroup of the isometric group of the universal cover. Okay, we choose a base point, x bar and the universal cover, and a symmetric generating set for gamma. Okay, moreover, I denote by gamma of S the growth function of the group, which is the cardinality of the ball of radius R centered at the identity with respect to the distance d of S. Okay, so by the general properties of fundamental group actions, I can find epsilon bigger than 0, such that all the balls of the form B epsilon of gamma of x bar. Okay, note that this is equal to gamma of the ball of radius epsilon centered at x bar are disjoint. Okay, moreover, the symmetric generating set is finite, so I can set mu to be equal to the max over gamma in S of the distance between x bar and gamma of x bar. Okay? Now the observation is that the ball of radius mu S centered at x bar in the universal cover contains at least gamma of S L of the form gamma of x bar. Okay? This follows directly from the definition of the word metric on a group. Okay? Now, this implies that if I enlarge the ball a little bit by a radius epsilon, okay, this is gonna contain gamma of S, these joint balls of the form B epsilon of gamma bar of S. Okay, and now I just need to compare the volumes of those guys. Okay, so I told you before that all these balls they can be written as gamma of the bar was here as gamma of the original ball centered at the base point x bar, and in particular they all have the same volume. Okay, so I can compute gamma of S times the volume of the epsilon x bar. Okay, the union of all these balls is contained into the ball of radius mu S plus epsilon at x bar. Okay, and therefore I get an inequality between the volumes. Okay, but now there is an important inequality due to Bishop, which says that if a manifold has non-negative Ricci curvature, the volume of the ball of radius r is less or equal than the volume of the ball of radius r inside the Euclidean space of the same dimension. Okay, so if I call omega n the volume of the unit ball in Rn, this volume is going to be less or equal than mu s plus epsilon times to the n. Okay, this term here is a constant, and therefore I get the sort inequality for the volume flow. Okay, any questions? Okay, we finish here for today.